All right, and welcome to this next video in the Integrated Math 2 series. This is our third lesson in Unit 1. Today we're going to focus on a function we talked about last time, which is piecewise functions, but we're going to do it in a lot more detail today. But before we get into piecewise functions, let's take a minute for a warm-up and see if you can do some of these using mental math. So take a minute to do that. All right, now let's look at these 6 problems. So we've got the first one, another radical, but this time we have a coefficient out in front to begin with of 5. So we're going to do the same exact thing, that only anything that we can simplify or evaluate the radical with is going to multiply with the 5. So let's go ahead and simplify the square root of 12. So again, we want to think about a perfect square that we can write as a factor of 12. So basically we want to rewrite 12 as the multiplication of 2 or more things, one of which is a perfect square. So let's see, 12 can be rewritten as 4 times 3. And the reason we did 4 times 3 is because 4 is a perfect square. So, so we still have the 5 out in front, but now we can actually evaluate this part of the radical. So, because we know what square root of 4 is, square root of 4 is 2. So this factor here simplifies, so square root of 4 is 2. So it's going to be 5 times 2 times the square root of 3. Because 3 is not a perfect square. So the square root of 4 is 2, and 5 times 2 is 10. So we get 10 square root of 3. So 10 times the square root of 3. All right, number 2, quickly estimate $12.07, $4.41, and $11.50. So if we put the whole dollars together, so 12 and 4 is 16, plus 11 is 27. And then if we go back to the cents here, we have just a few cents here, and then we have 41. So together those make about a half. And then with another half make a whole. So I know it's not exactly another whole dollar, but it's fairly close. So if you just are quickly looking at these numbers, you might estimate that your bill would be approximately $28. So just quick estimation skills there. Number 3, 2 to a negative first power. We've talked about natural numbers and how we can use the repeated multiplication definition. We've talked about raising a number to 0 and how that always results in 1. But what happens when we have negative? Well, let's continue that pattern we talked about in previous videos, where we have 2 to the 4th is 16, 2 to the 3rd is 8, 2 to the 2nd is 4, 2 to the 1st is 2, 2 to the 0 power, we said last time was 1. And then if we continue this pattern, so we look at to the right, we're dividing by 2 each time. So if we continue this pattern one more time, and we go one more step here in this pattern, we get 2 to the negative 1 is, well, divide by 2 again, and you get 1/2. So 2 to the negative 1 power is 1/2. And we'll continue to make more generalizations about negative powers here in a bit. But one word that's going to be coming up with that is the reciprocal. So a negative power will end up reciprocating the base that's here. So again, we'll talk about that more in later videos. All right, number 4, what is the function type here? Hopefully, going back to a couple of videos ago, you remember that this function type here is an exponential, but not just any exponential, it's an exponential decay, because it's decaying over time. Number 5, 102% of 40. So quick number sense, 102%, that's a little bit above 100%. 100% of a value is the value itself. So if we're a little bit more than 100%, it should increase. So 40%, our answer should be a little bit over 40. All right, so then let's take our strategy that we've been working on here. So take any numbers involved and then take off the trailing 0. So 102 times, we only need the 4 here. 102 times 4. One strategy there is, instead of multiplying by 4, is to multiply by 2 twice. So 102 times 2 is 204, times 2 again is 408. So Is our answer 408? Does that make sense? No, it doesn't, right? We said it was going to be just a little bit over 40. So again, we're going to move our decimal back. So is it 408? Is it 40.8? Is it 4.08 or 0.408? Which is it? Which makes the most sense here? And obviously that's going to be 40.0 or 40.8. All right, number 6, 126 divided by 4. Again, similar strategy here. We can divide by 2 twice instead. 126 divided by 2 is 63. And then 63 divided by 2 is going to be, let's see, 60 divided by 2 is 30. And then 3 divided by 2 is 1.5. So add those together and you get 31.5. All right, so hopefully that was a good warm-up. Let's go ahead and hop into our activity for today, which is all about piecewise functions. So our goal for today is to understand how to graph piecewise functions, including absolute value functions. So let's get into that today. So our first definition here is what a piecewise function is. We've talked about it before, but here's what it is. It's a function that behaves differently based on the input value, or x value. So where you are along the x-axis, it changes what your graph is going to look like. So that's kind of what that means there. Here's what a piecewise function looks like algebraically. I know it looks kind of weird, but let's kind of think through what this might look like. So here is another piecewise function, so a different one here. This is f of x. And f of x is defined in 3 different pieces. So we've got a linear function here with a negative slope, y-intercept of 5. But it's only going to occur for all x values less than or equal to negative 1. So over here, right, you're gonna obey this function. In between negative 1 and 2, so in here somewhere, you're going to obey this quadratic function. So you're going to square the x value, then add 1 to it. And then all x values greater than 2, so over here, you're going to obey this function, which is an absolute value function. So the graph right now does not adequately display what we're doing here. So let's fix it. Because right now we see the full functions, all 3 of these, but we only really want part of them because this overall piecewise function still needs to be a function. So let's remember our definition of a function is every input has exactly 1 output. Right now, every input has multiple outputs. Like for example, if this is all one part of one graph, 0.5 or something right here has an output of maybe 1, but also maybe 3.5, but also negative 1/2. So these combined do not form a function right now, but we can restrict what we call the domain of a function for each one of these so that it comes together to form a function. So let's restrict this red graph, the linear function, to only be to the left of negative 1. So I'm going to drag the domain, and we're not going to see the whole graph. We're just going to see to the left of negative 1, which is right there. So the scale is actually up by 2, so this is actually negative 1 right here. So for all x values less than or equal to negative 1, so all x values to the left of negative 1 follow the red graph. And you can see all the x values in red right here. So it goes from negative infinity all the way, and it ends right here. So all these x values are obeying that function right there. All right, and then in the middle, from negative 1 to 2, so let's fix the quadratic. So this quadratic, we should not see the whole quadratic. We should only see it from negative 1 to 2. And let me explain kind of the points here, or the dots. So because this one was less than or equal to -1, at -1 the point is here. Whereas the quadratic was greater than -1. So x is greater than -1. So starting at -1, but not including -1. Because at -1, again, we can only have one output value. That output value at -1 is way up here, not here. So that's why we have the open circle to show you that like it's not existent right there at that one point. Okay? But at -0.999999999, we do have a value there. So again, we've got to make it to where every input has exactly one output. All right, and then lastly, this absolute value, we've got to restrict it to only values greater than 2. Okay, so at 2 and onward, we're going to follow this absolute value function that we've set for us here. Keep in mind that because this one was in between -1 and 2, but including 2, that's why this dot is filled in, or circle is filled in. Whereas the absolute value is all x values greater than 2, so at 2, it's not included. Just everything beyond 2. So 2.1, 2.2, 2.3, and so on. All those values there. So now that we've restricted the domain of each one of these graphs to reflect what we have here in this piecewise function, now we've actually got a function. So every single input has exactly one output. And I've outlined the part of x-axis that corresponds to each one. So the x-axis from -infinity all the way to here corresponds to the linear. In between here and here corresponds to the quadratic, and in blue all correspond to the absolute value. So you can kind of see what part of the x-axis and how that's broken up for each one of these three. You can have however many pieces you want. In this case, we have 3 different pieces, but you can have 10 pieces, 20 pieces. In fact, there are certain functions called step functions that have an infinite number of pieces. They're not all written out like that, but there are an infinite number of pieces. So there's something to keep in mind here, that we have these piecewise functions. They can be kind of challenging because you've got the filled in circles and the open circles and the different pieces there, but that's kind of the overall idea. All right, so up next, we're actually going to look at something called an absolute value function. So let's create a grid page here, and let's dive into absolute value functions. So the typical absolute value function looks like a V, as we've talked about in previous videos. It looks like a V shape. And that the parent function, or the most simplistic version of an absolute value function, looks something like this. Where the left side has a slope of -1, the right side has a slope of +1. So this traditional absolute value is actually a piecewise function itself. So I know we had one kind of within the piecewise function earlier, but this is actually a piecewise function itself. Let me explain. We can actually write this. We'll call this f of x, I guess, again. F of x is equal to, and in this case we have 2 pieces. To the left of the y-axis, so for all x values less than 0, we obey this function here, which has a slope of -1, so -1x plus 0, because it's a y-intercept of 0. So this is the left side. Now the right side is the same, but with a +1 value for its slope, so just 1x. For all x's greater than or equal to 0, and it doesn't really matter which one of these you put the equal to on, because they're at the same spot, so it doesn't really matter. But that's how we can define an absolute value function using piecewise notation. Now you could also just write this f of x equals absolute value of x, and everybody would know what you're talking about. But I wanted you to know that absolute value functions are piecewise functions. We just have special notation to denote what those look like. So anyways, let me give you an opportunity to see if you can graph one on your own. So take a look at this graph here. Take a moment, grab some graph paper, and see if you can actually put this together, where you're dissecting the graph into 3 different pieces in this case. Keep in mind that this is still a function. It's just y equals 2, which is a horizontal line. And then the other 2 are linear functions. So see if you can maybe start with the full graphs and then kind of maybe erase what you need to restrict the domain. So see what you can do. All right, so let's take a look at the graph of this. Before we do that though, I want to explain how Desmos works. So if you haven't used Desmos before, it is one of the best graphing calculators that you can use. What I've got here is I've got the graph of x squared, and I want to show you on Desmos how to restrict the domain. So what you'll do is you'll type in next to the function, if you can see my screen here, you're going to type in the curly brace followed by the restriction. So in this case, I'll do like x is less than 2, and then close your curly brace. So you can see that the graph is restricted to only being shown between negative infinity and 2. So it's restricting that domain to all x values less than 2. Now in Desmos and other calculators, the filled in circle and the open circle don't really naturally just show up. So you have to kind of do that yourself. But that's kind of how we manipulate it in Desmos. If you want to have it restricted on both ends, you can do x is less than 2 but greater than -5 or -3 or something like that. So now you've done -3 is less than x is less than -2. So if you want to sandwich x in between 2 values, you use the less than signs, and that'll give you that graph there. All right. So just kind of a tip there. All right. Let's go to the graph of our problem just a minute ago. And here's what it should look like. So let me turn on projector mode here so you can see it a bit easier. Okay, so from all x values less than 0, you're graphing this linear function here. It's got a y-intercept of -3, so that was kind of easy because it actually starts on the y-axis, so we were able actually to see that. So it goes from negative infinity all the way to 0, open circle here because it was less than 0. And then y equals 2 is from 0, including 0, all the way to 4, but not including 4. So, so you have this horizontal line here at y equals 2, it's a horizontal line, and closed circle there, all the way to 4, and an open circle there. And then the last one was another linear function with a negative slope here from 4 to infinity. And it was greater than or equal to 4. So that's why the filled in dot is there. But the cool thing about this one is this part of the graph is what we call continuous, meaning I didn't need to pick up my pencil to continue this piecewise function. Whereas over here, I did. So this is not continuous over here, but over here, it is. So that kind of gives you an idea of how to graph piecewise functions. Hopefully you were able to do that on your graph paper. Excuse me. Let me give you a real world context in which piecewise functions occur. I showed you one maybe a session or 2 ago. Let me show you this one here. So this man is climbing up and then he's going to slide down this slide. So what you want to do is you actually want to model his height of his waist over time. So again, we're having 15 seconds on the clock here. And 0 to 10 seconds is the scale, or 0 to 10 feet is the scale along the y-axis. He starts out, his height of his waist increases, and then it kind of stays flat for a bit, and it goes down, and it stops for a second, 3 seconds maybe, and then he goes down, and then his height actually raises just briefly at the end. So take a moment and see if you can actually graph what his height might look like over time. I'm going to play the video again in the background as you're doing that in slow motion. All right, so just that last second that kind of increased there at the end. All right, so let's take a look at the answer. So what might his height look like? So it's constant at the beginning, then it was a constant rate of increase, and then it was flat for a bit, and then it went down. As he sat down, then he stayed still for a while, all right? So time is still going on, but his height was still consistent. And then he went down the slide, and then at the very end, he stood up. So this is actually an example of a piecewise function. Let me actually back it up here. Oops.
Hey Jason, how do you make clone effect?
Let me back it up here for a second. Okay, so as we look at this video here, this graph, so he was standing there at the beginning for about a second, and then after a second he started climbing the ladder, and so on. So let's look at the pieces here. So the first piece would be a constant function, just y equals 3, between 0 and 1. So 0 less than or equal to x is less than or equal to 1. And then from 1 to about 5.5 seconds, we can maybe create a linear function that models that part. And then between 5.5 and about 6.5 or so, maybe another linear function would fit that pretty well. And then when he sits down at the top there, maybe an exponential decay might be a good fit there. And then y equals maybe 6.5 between 7 seconds and about 12 seconds. So we can use y equals 6.5 as our function there. And then maybe another linear function here, and then maybe like a quadratic here between maybe 13.25 and 14.25, and then maybe another part of a quadratic function there maybe. So there's quite a few pieces there, but we can actually come up with the various pieces that form that graph. So hopefully that gives you an idea of how we might see a piecewise function in the real world. When looking at different quantities and how they change. So that's it for this video. Again, hopefully our goal was reached today of understanding how to graph piecewise functions, including absolute value. We're going to look at absolute value in more detail in our next video.